Okay, we're a few minutes past. Can you hear me, Faisal?
Yes,
That's good. Okay, hello everyone. Welcome to a new webinar session. It's my pleasure to have you guys on board today. My name is Alan Murgues. I am a consulting reservoir engineer here in Australia, and I am the founder of CrowdField, a digital hub for oil and gas professionals. This webinar series is an opportunity for me to sit down with experts in their field and discuss an interesting topic. Today, we're going to be talking about assisted history matching, an introduction to complex modeling workflows. My guest today is Faisal Al-Jenaibi. He's a Reservoir Simulation Engineer Advisor at RFD. He has an impressive 32-year tenure at ADNOC working on advanced dynamic models. He's led complex subsurface studies and history matching workflows. He's the contributor to many technical reviews, field development planning, and knowledge sharing initiatives. So it is my pleasure to have him on board and share his experience in this field with all of us. Now, before handing over to Faisal, just briefly a bit of housekeeping. We have about 40 to 45 minutes for the talk and some 10 to 15 minutes for Q&A at the end. Please, guys, stay muted throughout the session. I do not have the ability to mute individually each of you. So if you have questions, please raise your hand with a little hand icon at the bottom of the screen and wait for my cue before unmuting yourselves just to avoid the noise. Now, this session is being recorded for later distribution. And with all of that out of the way, Faisal, please feel free now to share your screen and let's kick this off.
Can you see my screen?
We can see your screen. Just go in presentation mode.
Okay.
Perfect.
Okay.
Yeah, we can see and hear loud and clear. Take it away, mate.
Thank you very much for joining us. I will talk about assisting history match technology, tips and tricks, how you can minimize it or get maximum of this technology. When we talk about assessing history match, basically we are looking for speed up our history match process to get the best result out of that. So when we are talking about assessing history match, mainly we need to address what the problem in the model. This slide is showing the most challenging topics when we are doing any simulation model history match. And you can see they are very hot topics, very complex element. It would take time usually to assess all these elements. And if you, unlike if you have many of these challenges coming into your model. Of course, we cannot tackle all of these in one go. So you need to kind of prioritize your issues in the model to take them gradually improving in the quality of history match. In general, as rule of thumb, anything related to the permeability, such as relative permeability, transferability, connectivities, are the most sensitive element, meaning that if you change the permeability slightly up and down, you will see a huge impact on the quality of history match. While the others, you may change them and they may contribute in the improving or the history match, but not as the permeability. So permeability and KV over KH, relative permeabilities, transferability and connectivity are very sensitive to the middle history match, and they are the most difficult part of getting a history match. More or less, I would say that as the RFD, we do have some technologies cover, let's say, 90% of these challenges. And of course, these technologies supposed to be quick, very fast, very efficient. We can do it in no time. As example, I was looking to one of the model which has a fracture. I just building ADFM for it to introduce kind of flow through the fractures. So, but in order to start any project of assisting history match, there is a mean you have to do it, or a step you need to do it. You need to make sure your model is running very quick. Otherwise, the whole project of assisting history match using it will be failure. Because if you have limited resource, let's assume that you have cloud or workstation or laptop, you can do assisting history match on this element. However, if they are having limited resource and you have your model is very heavy, very detailed one, we talk about millions of grid cells, it will run very, very slow. In order to get the benefit of assisting history match, you need to kind of coarsening or upscaling your model to make it run faster. I know some people will say, okay, by doing coarsening or upscaling the model, you will lose the resolution of the model. However, at this stage, in the beginning of any project of assisting match, what you need just to let the model running as fast as you could. That's the main objective. But later, once you get closer or customizing your variables, then you can remove those coarsening and let the model to come back to the original grading dimension and size. So in this example, I will show you a model which I have received around 6.6 million has been coarsened, upscaled to 100,000 grid cells. I'm still honoring the same fluid in place. The model is running, it was running from 4 to 6 hours, original 6.6 million, now it's running in 10 minutes. The purpose of that, I want to do as many jobs, as many iterations, I want to assess as many variables in the model in the beginning until I reduce the errors as objective function. In order then I can use that model to clean it and remove all this adjustment to get the final runs. In general, there are many techniques how to build or doing an assisting history match project. But I will share with you 3 techniques, standard one, which I have seen it and most engineers, they are doing it. The first technique is called multi-realization parameter approach. Basically, in very simple manner, you're going to generate a let's say, petrophysical input data, like let's say 10 realization of porosity, 10 realization of permeability, 10 realization of structure models, rock typing, whatever parameter used in the dynamic model. You generate these from the static model with support from geoscience people. Then same thing from reservoir engineer, he will generate the input data as many the parameter or iteration he needs. Generate like 10 iteration table for the same, define the 10 maps of regions, BVT, fault sync system. So it's ready-made from static model and dynamic model. They are generating this, what we call input data one time, and they create it and give it to reservoir engineer where he merges them together from static to dynamic, compile them together using assisting match. Randomly could be or selective. He take one realization of permeability, one realization from rock type, one realization from porosity, use them in the simulation model to get result. Then he made another iteration with another let's say properties from porosity, permeability, rock typing, all the other parameter, and he's doing like that. So it's fully depending on the geoscience people, and he get his output from the static model in one go. So once he getting those, let's say, multi-realization parameters, he doesn't need anymore to go back to the static model. So it's one go, one time. The second approach, what we call it single realization. Single realization, it's more like iteration between static and dynamic and assisting history match. So in the beginning, the geologist, he will provide the reservoir engineer with a one porosity map, one permeability map, one input data, properties data, one time. And same thing from reservoir, he will generate those input data like BBT or SCAD data and faulting system, everything, he set it in one time. Then the integrated assisting history match tool will compile these elements together, do run. The output of the simulation run will be sent it back to the static model with a new, let's say, adjustment from the assisting schematic to tell me an example, you need to use permeability multiplier in this region or that regions. And the tool will advise the static model to regenerate another permeability model based on the finding from the previous run. So it's kind of more like looping between static and dynamic with assisting schematic. This approach is preferred. However, in order to use this approach, you have to have both static and dynamic tools online. They should be continue running, and that's sometimes it's become very heavy, especially if you need to do a lot of iteration between static and dynamic. Okay, the third approach, which also used in many regions, is that what we call it parameter functional design, which is including, instead of having, let's say, properties as a 3D properties coming from static to dynamic, we are using formulas or mainly Python system. So we design our comments, the input data in the shape of the formula. If the porosity, this is the porosity, this is the water cut, could be the rock typing, and out of that you can use the regression lines, simple one, to generating a permeability, an example. And you can see that putting a porosity permeability relationship as the generated as a scripting, where I'm testing the shape of the porosity permeability relationship on the history match. So it's changing the slope of these correlations, the wideness of that, and how it's changed with the rock type, something like that. So these three concepts are the most domain approaches used for using assisting match. There is no recommended approach. It's up to you, and it's case by case, depending on the number of variables, how fast are the resource you have it to take in care. Now, by having this concept, I will explain to you how usually we are doing, what's parameter we are do it. So in this example, I took a model which have X number of wells. And first thing I created in that model is called what we call it a well region. Well region basically it's a body, discrete kind of bodies around each well, and these defining an area in the 3D. So it's in from top layer to the bottom layer, or at least the interval which the well is perforated. Then, what is the reason of creating this well region? The main objective of using well region is that you can change some properties within the well region without affecting the other wells, especially in the Middle East, because we have supergiant, and we don't expect to see the same properties all over the whole reservoir from east to west, north, south. It's the same properties. And I'll give you an example. Let's say rate permeabilities or rock type properties or something like that. We don't expect to see the same rock type classified all over the model. It's the same everywhere in the reservoir. It will be changed based on the location. So it's at least well region will give you some kind of freedom to readjust your properties only around the wells. You don't need to create affecting the other wells. So the tool, by creating this well region, will use that well region to readjust the properties within the well region without affecting the other, and the other also will continue doing that. Of course, the tool, some tools, assisting much tool, once getting a good result, they are freezing let's say the parameter using within that region, while it's continue doing enhancement work for the region which are showing very bad, let's say, objective function. Mainly the objective function is the difference between the actual data and what the output of the simulation run with this parameters been adjusted. So at the minimum objective function values, meaning you have better and better result matching the data. Now, in this example, I'm using what I call it arithmetic system. Within the data, we classify some variables. We said, okay, I want to use a permeability within this range. So the first column representing the base values, which we'll start with, and the second column represents the minimum and the maximum. As an example, I'm changing now permeability in this model with these variables. I will show you the formula by itself. Okay, now I'm changing a constant CA1, CA2, CA3, continue with between maximum and minimum per each one. And then I will use this one into creating another parameters, which is, let's say, E20A and F and G20A. Now, what's happened? I'm creating these things element for test for modifying the permeabilities, but I want to type permeabilities within the porosity. Of course, we have more sophisticated workflow, but I try to make it as simple as possible. In the beginning, we use this approach whenever we are assumed we don't have a proper permeability model. So I'm using porosity to generate permeabilities, to create also correlation with the rock types, ultimately to start with the porosity and water saturation. That's the input data, which will guide all the other parameters used in the dynamic model. But of course, the ultimate goal is to approve the concept of using only porosity and water saturation against higher aquifer water level with a rock type classification to give you best history match end of the day. So in very simple manner, this is my formula. So my formula is very simple regression formula. It's a function in porosity at the moment plus the porosity ranges. Why we do? The reasons we do that is just to grouping or creating, let's say, a porosity permeability relationship with the pair, let's say kind of rock type classification. So the blue line or the blue numbers represent the best rock types, highest porosity, high permeability. As we are moving from the highest values to the red one representing non-reservoir or tight, very, very tight rock properties. So that formula, which I use it in the beginning with the porosity, we started using it to generating this kind of relation. But this is with the simple, defined, let's say, the variables. Use it in the regression formula to generate this one. But what if I want to change the permeability? I want to create different kind, or I wanted the tool, the assisting system must start changing the variables to see what possible shape of the porosity permeability relationship to be used for assisting history match. This is another example by changing the variable used for creating the relationship between porosity permeability, color coded with what I call it rock types, or some definitions of from good rock types to tight rock type. In my exercise, in my models, I usually use thousands of variables to control everything. And the whole my vision objective is to shaking the model. I want to check the input data in the model up to 20% up and below the proposed range, just to see how far I can go and what is those parameters can affecting more on the model. Of course, end of the day, by using that tons of variables, you need to sort them out to see from the most sensitive one to the lowest one. Of course, the best technique is using tornado chart, starting with the highest impacting parameter to the lowest, and you can focus on the top, let's say 10 variables, and try work on them further and further to improve the quality. So you see now, this is the expected effect of the shape of the porosity permeability relationship per what I call it rock types, based on those variables I'm using in them. I just show you as an example. Usually they are continue. And usually the assisting history match tool changing these parameters gradually. Of course, there is two type of data we are using in the assisting history match. One of them is what we call it real values, changing with the decimate, or with the numbers with some decimate numbers, it's going up and down smoothly. The other, which is discrete parameters, integer, and they are just 1, 2, 3 like that. So it's changing a table. Like I want to introduce a table into assisting history match tool, I say table number 1 or table number 5 or table number 6. So it's very discrete. Okay, let's go back to the same model now. And so the first element I am changing it in the history match, I'm changing the parameters per region. And it's not only parameters in one dimension, it will be in the 3 dimensions. So I'm changing parameters in X, Y, Z. Within that region, belong to that region, which I know is belong to X number, X will number. I know it. So I'm telling the tool now, go and take the permeability within that region, change the permeability in X, Y, Z directions. And usually, perm Z is a function in both permeability X and Y, because now I have 2 different permeability. One is in X, one in Y, and they are completely different in some locations. So how I don't want to use perm Z generated by perm X only. I want to also integrate it with a perm Z, perm X. So I came with this simple formula. It's a function also in perm XY as a KV over KH ratio. And I can create KV over KH per region instead of using one global KV over KH all over the model. Now we can generate it as also function in the region. So region definition is very important, which really help to break down your model into segments, areas where you can play with them separately to try to get the mess. Of course, in the beginning, I don't recommend it to use wide range of investigation ranges you are using applied for permitting an example. You start with a small one, reasonable one, and let the tool to do a lot of runs until you are coming with something better shape of, let's say, the history match profiles, including with the objective function. I will talk about more of that. Now, we are doing, we are changing the parameter in XYZ within the within the region, and also we can do it per each layers. So in the whole layer itself, I can change the parameters in XY directions, and I take it up or take it down. Then within that layer, of course, we do have this will region. I can take then will region within that layers, which I push it up or down based on the assisting command to remodify its permeability a little bit up and down. So you can see now I have 2 dimensions for the permeability change. One is per region within around the will. Second within the layers itself in XYZ direction. So this is the one of the driver how to change the permeability. Okay, now also I'm showing, I'm putting the script usually for the user. So if you get this presentation in the future, you can use the same concept of setup of how to design your arithmetics or let's say the Pythons to say, okay, I want to change the parameter up and down per region. So an example, I'm putting that. What if my region number 0, which is the aquifer usually, it's around the reservoir, I'm changing the parameters, whatever parameter existing, multiplied by 10 to power of the value which I want to change it. So I know this this code, let's say this region parameter adjustment, I know it belongs to where location. So in the future, when I do a complete history match and I have one problematic well which is showing very bad history match, what I do, easy, very easy, just to know which well based on the history match profile, I immediately know where the which code is belong to that well, and I come and remodify it. Maybe he doesn't need to use a negative -2 to +2. By the way, -2 and 2.2, this representing a logarithm scale, which is -2 meaning 0.001, I think, and 2 is around 100, 2 zeros. So you see now, instead of using real numbers, let's say I want to change the parameter from 0.001 to 1 to 10 to 100. Usually, most of the tool, if you are using these kind of numbers, always they go into the highest values, the highest, instead of taking the lowest 0.01 or something, they always driven to take the highest number, which is let's say 50, 20, 100, somewhere between those large numbers. So when you are using, this is one of the advantages of the tool which I'm using. It will allow me to use real numbers, very simple from minus to plus, normal one, but they are to the power of 10. It's already converted to the logarithmic scale. Okay, now the workflow, how I'm getting you. Now, the first thing, I have well reagent. Of course, now I have 3D water saturations from static model. Then there is a new workflow, another workflow we are developing here with the rock dynamic. It's called for fast track approach to design water saturation. And it's very powerful in the way that it will take the log water saturation, whatever shape, with the tilted contacts, with the multi, let's say, compartmentalizations, with any shape. And it will generate a PC curve to replicate that water to generate what we call it water SPC. And then we use this one, basically the water PC into the dynamic model to continue doing a history match. This is the static model, this is the dynamic rock type, which is came from the water saturation and porosity through our workflow to generate, let's say, the input data for the dynamic model. Correlation between SW log and SWPC, you can see it is fitting in the 45 degrees. Now, the thing that you have to keep in mind, the geologist or geomodeler, he are willing to give me, let's say, B10, B90, B50 cases of water saturation and the 3D distributions. The tricky thing, you cannot generate every time whenever you get a new water saturation maps from the geologist, you need to redoing the whole skull frame where work to try to reassigning the PC curve to match it with the log water saturation. The workflow which we do have it, fast track, is so simple. It's run in second to read the water saturation, the new water saturation, the 3D coming from static model, and it automatically regenerating the SWPC to taking that and use it into the assisting history match. So these are general input data which required to be used with the assisting history match. As I said in the beginning, we are using wood regions to redesigning my permeability. So with this input data to the dynamic model, I'm getting another different relationship of porosity permeability, because, as I said, porosity permeability are the most sensitive, are the most effective parameter on the history match. So I get different, let's say, realization of permeabilities based on the variables I'm using. If I use very high range of radius of, let's say, the parameter investigation, I will change the permeability widely, very high. Or I can change it very small, like in this greens, same like the original permeability. So this kind of the setup usually to use it in the assisting history match. I show you up to now as kind of routine work, framework for assisting history match. But we want to complicate the issue further. Let's assume we have 5 rock types in the model, and I have 5 drainage curves, PC curves, and another 5 imbibition curves. And the new things what we are currently we are using in our assisting history match technology, or we are applying in our model when we are using assisting history match, it's not only changing the permeabilities. As I said, we have permeabilities, anything related to permeabilities will show impact. So I'm thinking, oh, what about the relative permeabilities? In some regions, you may got a good history match in that region based on the shape of defined, let's say, best shape of relative permeabilities with the drainage and imbibition. But if you use this relationship of the relative permeabilities in different location in the field, you are getting a worse result, either high water or less water, or high gas or less gas, something different. So what if we can change the relative permeabilities per region also? So it's not only the permeability, which is a standard way to change the يعني, parameter input parameter for assessing it, but let's complicate it further. So I want to now, I have this shape of the relative permeability is fitting for that يعني red region, but I want to use different shape of relative permeabilities in the blue region. Based on the output of that region. I don't want to only focus on the permeabilities. I want to test another parameter, another let's say parameter effect on that try to improve the quality of the history maps, which is the relative permeability. By the way, relative permeability, you know that it's huge, have a huge impact on the water and gas mobility in the model. You can cool it down, the water, an example, by reducing the shape of relative permeabilities, the water will move slowly in the model, but still you need to keep less high permeability in the model because you are matching with the pressure or something like that. So now I have a new dimension, a new parameters has been introduced to change within the history match. And let me explain to you how the system or the scripting, and basically the arithmetic, which is the very powerful feature in that simulator, which I'm used to give me the freedom to change it automatically, also through the assisting history match, where the assisting history match is going to test the concept to see how does it work. Now, I will generate 3 sets of the shape. By the way, this is one single rock types. Rock type number 1, and it have 2 different shape of relative permeabilities. The one is very strong water mobility. The second one a little bit cold water mobility. But I will show you more example in that. So I have now, I'm generating saturation table for my input data in the simulator. So I tell you, I have 5 rock types. The first saturation table from 1 to 5 representing drainage. From 6 to 10 is representing the imbibition. So this is a complete set of the input data for the dynamic model. I took this table and just I remodified the shape of relative permeabilities without changing the PC curves, because if I change the PC curve at this stage, I will change the fluid in place, which I don't want to. I just want to change the relative permeabilities to accelerate or slow down the fluid movement within the model. So then I will need to create another set of the data. So by editing, I observed my tables ranging from 1 to 10, the maximum. Now my next table will be starting from 11, meaning that 1 plus 10, those numbers, it's become 11 to 20. That's another set of data. I just take it and put it in the, follow the first table. Then I create another set, the third type, which is become from 11 by editing 10, those original one, is become 20, 21 to 30. So total I have 30 tables representing different set of relative permeabilities from, let's say, high water mobility, intermediate to low water mobility, or to gas, where I will let the assisting history match testing those tables to see how they are impacting on the history match. Now, in order to use them, I need first, this is an example of the same rock type, dynamic rock type number 1. This is the oil water system, this is gas oil system. Now you see the first, the first rock type, by the way, all those representing one rock type. The first rock type, I put it as very strong water mobility. I want to make the waters moving very quick. Second one is an idle. It's just up to 1 relative permeabilities. The last, the third options, I want those group of, I want them slow down the whole model water in the model. By the way, this is all, as I said, 1 rock types. Usually, the other rock type, the rest rock types from 2 to 5, they are following the same trend. The next work type is coming down a little bit, and the third and fourth, I'm defining the first rock type as the best rock type, the highest permeability, the highest properties. This is the same for relative permeability for the gas system. And now I want to use those with the assisting history match. How to do it? We defined a code. I call it KRW 012. 0 meaning is only using this, immediately he's going to use those tables, which is representing very high water mobility very high, or could be opposite. When I move water, I slow down the gas. Or if I slow down the water, I push the gas to be more efficient. Now, by using 0, 1, 2, I'm meaning that I'm tell the tool or simulator use this table if the code is 0, 1 use this table, 2 is using the last table. In very simple manner, again, by arithmetic, I say that to the tool. If the region number 1 or the area which I am looking to, X, let's say, let me take the second one. If the region number 1 belong to well number A, now setnum, the original setnum plus 10 and multiplied by this code. If the code is 0, the whole this element becomes 0, meaning he's only using whatever original setnum or the first table. This one, this is the input data. So if I want to use an example table number 2, so I will say setnum, the original one, this tables plus 10 multiplied by 2, which is now those number, this side of the formula, they become 20. As if like I am using this table, but I adding to all the numbers plus 20, which 1 become 21 and 5 become 25. Very simple formula. It will allow the simulator to pick randomly or based on the assisting image to decide which table it will use within that well region. And that by that I can do more sophisticated framework to do that. Not only that, but also I can now within another scripting I do, I can select table 1 of relative permeability for the oil, use it with this table number C for the relative permeability for the gas system. So I can now randomly or through assisting estimate, I can select table number A with the B for gas, or C with a water system with A with a system of gas. It can jointly combine them together in the same table, use them in the simulator. But again, I'm not changing the PC curves belong to those curves. So all of those curves are used, they have to use the same, let's say SWIRR, using the same. Although the shape of the curve are changed based on my needs, I want to speed or slow down the water, but I'm telling the tool, please use it all in the same, with the same PC curves. So this is something not being tested widely in the assisting much. We do have a workflow. It's very simple. Usually take me half a day just to build these workflows in the model. Now, the second advance or second new element we are introduced, in some wells, doesn't matter with the well region, doesn't matter you playing with the permeabilities, you playing with the rate permeabilities, it's not producing the right volume of water or oil or gas. It doesn't matter, and you don't want to divert out of, let's say, physics. So what we said, okay, maybe there's no enough hydrocarbon exists around that well. Maybe, or there is more hydrocarbon exists around the well, it will slow down the water movement because there is more oil. So we need to change now the volumes of hydrocarbon around, let's say, within this well region. And I am showing this example. I have asked your modeler to give me B10, B50, B90 cases. Each one, they have different fluid in place. And all of them, they are honoring the data at the well location. They may have different contact, different petrophysical data, let's say porosities, structure, whatever. But they are representing different fluid in place and from geological respect, B10, B50, B90. And we do have our own well regions. An example. What we do, we found a way now to change, after we reassigning the relative permeabilities, we can go back and look into the model to see which of these wells are suffering, let's say, from extra oil, an example, or more less water cut. So I need more to get more water into this well. meaning that I want to reduce the volume of hydrocarbon, meaning the best way to do that, let's take that well, the rock typing around that well from B10, B90 case, which have less oil in that place, within that, around that, everywhere in the well. If I want to increase, let's say, oil production, I get a lot of water immediately to, let's say, from the wells are close to the contacts. And I don't want to play too much in the permeabilities, or whatever I do in the permeability, I still am not able to get that water. I was talking about the oil. I want to get more oil from that well. So I want to change the fluid in place around that well only by looking to, again, B10, B90, B50. So I want to change the surrounded fluid in place for that region from B10. And we done that automatically within a system mesh to basically to load all these, whatever, let's say, Bs, fluid in place models, complete set into the simulator. And then the assistant match will go and check the final history match, the base case, and it will go and change the, let's say, the oil around the wells. And the beauty of this exercise, we are only need to change the, in order to change the volumetrics around the well, we are changing the signed rock types. Not only that, but we are using the same script of generating the PC in all these cases. So if I get this P10, an example from, I run the same script for generating the PC curves or to sign the rock types belong to this region, similar to if I want to use it with the B90 case. So by that, what it's doing, I'm changing, let's say I redefining my rock type in my PC, which will give me the same volumetrics, but I'm not changing the shape of the PC curve itself. I'm just resigning the setnum, which will give, if I use it, it will give me B90, B10 volumetrics. Then I go to another B90. I will just resigning the setnum, which will give me the volumetric of B90. Now, the associative match, based on this well region, it will start changing the setnum around each well in the way it will change the volumetric. Now, let's see this example. In this example, the tool, it decided to change the oil in place around this, let's say, those two regions, I think, the blue one and this one. And it's he's picked from, I would say, B25. He reduced volumes around these to cool down the, let's say, example, to speed up like water cut, an example. In the other region, he putting green one, he take from B90 case oil around this region. So you see now we are introduce more and more complexity into the tool. We start with the normal permeability adjustment, then permeability per regions, permeability per layers. Also, I do have permeability globals to change it. Then we are coming to relative permeabilities. We change it per rock types, change the relative permeability. Then now we are moving with the saturation, the PC curve itself. So you see how much complexity we are introducing to this system. The whole objective, of course, to get the better result. Just I put a message here that if you do a history match with model take you very long time, don't wait until the end of the run, because in many occasions, if you know that this run it's going out of let's say the limit which you defined. Like an example, the reservoir pressure is dropped below 1,000 psi, and if, from your expectation, the reservoir pressure should be higher than 1,000. So you can put addition comments within the data dig to kill the runs. Once you start divert from the out, let's say, limits you are defining. Like water cut, if I use this variable, my water cut is start shooting up too much, I don't need to wait until the end of the run, then to kill the job to start using. I just put some more constraint within the data dig to kill the jobs very at earlier time, where I can use these CPUs or the hardware resource to submit additional runs. Physically, you by that you will only try to maintain the right jobs or the job representative job, while you terminate or remove the jobs we are expecting to see very bad result. I have to run because of timing. Okay, now we are changing so many things. And let's say we are, of course, we're coursing the model, we run it. Let's assume that I came with this kind of permeability fitting in the model, which give me a good history match. But it's going out of no geological inputs become, no physically. I mean, it's kind of let's say pull eyes, localized adjustment. Like this one, you have very high permeability in somewhere in the middle or belong to that region, which is belong to this rectangle, and it's not showing a very nice shape of the, let's say the final one, which I like it, or something become more geological representative. What you do, you just using assistive match until you come with the best variables. And the variable, he tell you, okay, I need high permeability in the middle. I need high permeability in this area in the X direction. Maybe in the Y it could be slightly higher, something like that. But this is the shape of the, let's say, permeabilities, only permeability at the moment I'm talking that, which give me a good result. So I want to replicate it, but I want to honoring some, let's say, more geology sense in this manner. So what you do, the tricky thing, what you do, you create a dummy wells all over the model with some well spacing between them, let's say either 500 meter or 100, let's say 1,000 meter. And those dummy wells will read what in the static, in this final result at that location in terms of the permitting X, Y, Z. Then you will have this parameter within that, those dummy wells, and they are in the equal distance. What you just need to do, use your geological software to republish or redistribute those parameters. Now you see, now we are moving from more like cubes or bodies shape of parameter permeabilities to more like geology sense. And that's the tricky things you can do it. And you can do it while you are doing an existing history match, or you can wait until end of the runs once you complete as many runs you have to get you the final things, and you do it. There are many ways to do that. Okay, now I come close to my finals. Let's assume I done my homework. I run thousands of runs. I getting the cloud around the actual data. I'm using oil rate as the main driver, or let's say control parameters. So I'm honoring oil rate. Water is up and down. Liquid, gas. Also, there are many runs around up and down, but they are so close. So I get a lot of things. I don't know now how to select or come with the best solutions. Of course, how does the system work in our tools or basically? We start with the wide parameter adjustment. This is objective function. As I said, objective function is basically the error between the actual data and what the simulator completed. Our tool basically, it can add loading a limited number of objective function. You can match per field, per well, per region, per let's say gas, oil, water, pressures. You can create your formulas if you want some correlations you want to. So there is unlimited objective function. You can load it into the tools. Now we start with I start with the global parameter adjustment. I came from high errors objective functions coming down to these values very low, and I want now when I reach these numbers of runs, I want to to not wasting time to do continue or adjustment. So I took let's say another set, and I took the best cases from out of those global adjustment. I use it to start with another let's say parameter, change them to start improve it further. So start further enhancing the runs and getting less and less objective function, which is meaning better result. And by the way, this circle or points is representing one summary value of the whole objective function. So if you're creating 10 of objective function, you want to match single oil rate, you want to match gas ratios, pressures, water cut, any parameters, the objective function in this tool will merge all of these to give you one single value end of the day. So each of these points represent one complete run from A to Z to the end. And he summarized, he told me, okay, that's run. He showed very large error. Most of parameters are far away from the actual. And as I move from the blue to pink, it's improve it further. Now, after complete this task, I took the last one from this, let's say, arrangement of the variables and add more variables into my runs to improve further. So I took this one of the last case from the pink to use it for the green. Start with the green and it's continue improve it until I get the last one. Of course, there is no limit number of runs you do. If you want to continue, let's say 2 years, you can continue. Try to improve it. It will continue to improve it as the variable to be changed and adjusted up and down. But the time is it's important. You need to get your result as fast as you could. And by the way, this objective was done in very short time. I think it was 1 month to run very complicated models with tons of variables, challenges, as brought it in the slide number 1. Now, in the second plot, this one is representing one of those cases. I don't recall which scenario, but it starts with the highest error, and this color code representing the well, meaning that the first run, one of the first run, this one an example, he showed me which well is showing the highest error, or let's say mismatching with actual. So as I'm moving from the highest run errors, where I still know, that's the advantage of this tool, I know which well, basically I know which well is showing me the most error to the lowest one. Now, you see now it's improvement. It's starting with the blue one example, I can know which well. He's starting to improve it with the time until he get the lowest. The same thing for the green, for the other colors. Some other colors not shown because the well is already shows the good result, so it doesn't show any difference or error. But here is showing only the wells will showing very high error, and it show how much improvement with the runs as I'm improving from higher objective function to the lowest. So it's another indication where I can immediately pick the last worst well. I just go and do it manually if I want to know. And this in the top one, I don't know which well is troublemakers or the well which show me very bad result. But in this plot, I can see it now. I can focus on that well immediately and work on it to the end. Of course, end of the day, with this objective function, with all these elements, we are going to summarize our runs to see or to pick only the best cases. I don't, main objective is not to carry out as much jobs in the day, and I have to make sure I'm surrounding the actual data. Let's say the top limit and the bottom limit of the runs is covering the actual data. So meaning the variables or the ranges of uses for the variables are very convenient. It's covering the, let's say, the cloud of the actual data which I want to know. And this is the end final result. You see, it is very nice. I'm not looking to also the well level. This is the field level, but also in this exercise, I'm looking to the well level. So individual well by well is improved, and the summation of that will improvement showing in the final, let's say, field oil, water, and gas rate, pressure also included. This is my last slide. In some cases, although we start, it's always recommended to start with a little bit wide range of limit, upper and lower limit, to allow the variable to be changed within those limit. But you can do that after a while. After, let's say, you make 10 randomly hypercube runs, you understand where the, let's say, the limit. And in fact, what the tool is doing is very simple things. He's taking the highest values of, I may go back to one slide. The tool basically, it takes the values of that variables from the highest case and the lowest case. And he said, okay, let me change that variables between those higher and lower case. And this is exactly what the tool is doing. So it's helped the end user to cut down the range of, let's say, changing that variables. Instead of using minus logarithm scale minus 1.2 to 1.5, an example, is cut it down to minus 0.3 to minus plus 4, where he will change these variables within that minimum maximum. And some cases, it's this is the base case, which he picked it as the best case out of the, let's say, the selected case I picked. In order to give this range as an example in this exercise, I just use, let's say, 3-4 cases. I don't need to use all the cases. Just to take 3-4 cases, let the tool to investigate what is the minimum maximum per each parameter, where you can customize it, cut it down, and let's say maybe you can select it with the range, let's say within 10% or higher or lower, to give you better result. And this is the tricky things. Of course, as you are reducing the, let's say, the radius, or not radius, but the range of investigations, you can get a very good result in the other model, which I'm showing you here. So, and this, by the way, this is case number 1, which is this one with these variables. Before starting running, very lengthy process. It's immediately, once I done those 3-4 cases in the Hypercube, I start doing optimization, trying to get the best result. This case number 1, you show me the best scenario. By this, I think I can, okay, I finished my presentation. Sorry to take you that much time.
Thank you, Faisal, very much. That was an intense pack with a ton of value there for sure. I think we're running a bit out of time, perhaps time for 1 or 2 questions if anyone is interested to grab the mic. If not, I just will ask one question here, and perhaps I can follow up on LinkedIn with the other ones that I got myself. But I think a comment, which will be followed by a question. The comment is that A in the AHM means assisted, meaning this is not a set and forget thing. You have to be on top of it all through the process. Submit a batch, observe, come and edit the objective function, change the ranges, change the weights, all of that. So it's assisted, so it requires your human input. But I was wondering if you have an opinion on how the algorithms perform when you approach the problem as a multiple objective function versus one objective function at a time on a sequential fashion. What's your preference, whether you have an opinion on multiple objective optimization?
One of the advantages of this tool, you can put a weight on which objective function. If you have multi-objective function, you can put on which of the objective function you want to weight, give them weight. So the tool will focus on that parameter as the number 1 and try to get it better and better. Like if you want to matching water cut, you can put, let's say, on water cut, give him weight of 2 or 5 or 10. And by doing that, the tool will be focused more on the water cut versus other parameter. Still, you want to honor them. And that's the advantage of the tool. Now, it's not only this tool, by the way, it's most of the tools that have all these features. I don't want to do kind of marketing, but I will tell you, most of the tools in the market now, they do have this feature. It's tool by tools. But the thing that is the human, let's say, how you can use these tools. Some tools can give you let's say strategy. You can do very complicated workflow. Other is so simple. It can do less simple to do that. It's all depending on, as I said, human, how you can use that tool. I can give you I can give a beginner as example, a Mercedes cars, and let him drive it immediately. So I give him very powerful car, very expensive car, to the beginner, just get a license to drive it. Or I can give him a Fiat, very small car, fit for purpose for his skills, to use until he become more familiar, or until he build his, let's say, experience in the driving. Then I can give him better and better. It's all depending on the human. Yeah.
For sure, for sure. Okay. Anybody interested in asking a question for Faisal? It seems not.
The beautiful of this tool, yeah, it's okay. Just a last my comment, the workflow or to prepare all these parameters, it's just a 1 day maximum. Yani I can do it in 1 day. All the specifications you see it in regarding relative permeabilities, basic curves, changing the fluids, using PT and B90, all these scenarios, all this sophisticated, usually we do it in 1 day because of the tool we have it, plus the skills we do have it. End of the day, most of the assisting history match projects, they take us between 1 month to 3 months, something like that. We never go that much time consuming doing something beyond normal time. And that's the advantage of using assisting history match. Yeah, thanks.
For sure. Okay, thank you, Faisal. Thank you very much, everyone, for attending. I think we're 3-4 minutes past. This presentation is being recorded, so I'm going to send the recording to all registered attendees, and then we can follow up on LinkedIn with additional questions that you may have for Faisal and continue the discussion. Okay, thank you very much, Faisal, once again.
Also, I will send you. I will send you the presentation in PDF file. It's
okay,
very
fantastic.
huge, so
there you go, folks.
I will share it with you the presentation. Yeah, thank
Great, excellent. All right, thank you very much, everyone, for tuning in. And once again, thank you, Faisal. Have a great day, everyone, and we'll follow up on LinkedIn. Cheers.
Cheers. Bye.